And so that search engine assignment is a very simple one, but it contains some ideas that are in search engines in general. So what we mean by a search engine is that we have a web page. So let's say we have a web page W1, W2, W3, and W4, and W5, and so on. So assume that these are web pages and they are connected to each other, usually by a directed graph. So the definition of connectivity in web pages, we define them as if W1 has a link to W3, like an HTML link, we say that W1 is connected to W3. So basically what search engines do is, like Google, Yahoo, Bing, they are much more sophisticated, obviously. But in a simple idea is that you go collect all the keywords in these pages. These pages have keywords, so you can grab the HTML, you can clean it up, and you can get all the keywords. So once you do that, you create sort of like a reverse index. So we call it a reverse index. Reverse index. And this process of getting keywords from web pages is called crawling. So you can start from W1, and because you know links to W3 and W2, you can follow them into other web pages. From W3, you can go to W4. As you can see, this is a directed graph. And so reverse index is essentially that you have terms. So let's say you have terms like term 1, term 2, term 3, and so on. So you might imagine that the term 1 maybe appear in W1 and also W5. Term 2 appears in W2. And we can also put some numbers in addition to the document. In this case, it's a web page. We can also put a number saying term 1 appears twice. So in your little search engine, what you're going to do is to really build a hash table of keys. So this will be a hash table. So when you're given a term, you can hash that and go to the list and find all of the documents where that word appears. So in terms of the way the search engines work is that you build this by crawling, you build the reverse index so that when you do a search, it doesn't do a real-time search. It just goes to this data structure and hash into the term and find all the documents where your search appears, where that term appears. So that's how it works. And then the next topic I'm going to talk about is what's called the depth-first search and the breadth-first search. Now, these are two traversal algorithms for graphs. Now, we have done traversal algorithms for trees, such as in-order traversal, post-order traversal, pre-order traversal, and so on. But now graphs, in fact, trees are graphs. Okay, so if you think about tree is a graph. So every tree is a graph, but not every graph is a tree, because in a tree you can only go one way, right? So, but if you have links back to root or something, then it becomes a graph. Okay, so a tree is a graph, and so what we're trying to do is to come up with two methods. In this case, for graphs, it's only breadth-first search or depth-first search to find things. And so we will talk about some of those ideas. The next idea we're going to talk about is something called topological sort. In fact, your next assignment will be based on this. You will be implementing a topological sort for after this assignment, after the search engine assignment, you'll be doing an assignment on topological sort. Okay. Any questions? So that's just the sort of the what we're going to be doing today, mostly. So we will try to come up with some problems as we go. And the little search engine assignment is, that's due. So I want you to make sure that you pay attention to the due date, because there are no grace period for any submission deadline. Because of this situation, it's very difficult to make any exceptions to that rule. And it's due on April 17th. You still have about 8 days to submit this. And the basic ideas are mostly, essentially what you're going to be doing is exactly what I talked about here. So in this case, instead of web pages, you have documents. So you have two documents. Let's say you have two documents here. You can call them A and W. And so you find the words in those documents, say deep and the world. And this indicates that that word deep appears in the document A twice. So essentially, you have to get a count for that word in that specific document. So you can think of this structure, that's the main structure that you're going to be working with, as an array of maybe a hash table of arrays. Okay? And I want you to sort of pay attention to all of these things that are very important. You should read them very carefully. And it says that you have to write your own driver to test your implementation. So you will have to do that yourself. And some things are already implemented, such as little search engine, and few things I'm just going through very quickly over this. So there are two hash tables. One is called the keywords index hash tables, which are the main words, like the important words. But the noise words are really things like da or or some common words that you don't really care too much about. Nobody search for those things. All right, so you have the noise words and then you have the keyword. They are both that you have to build. Okay. And I think you must test your program with more than just the two files provided to you. And in fact, the best place to find good text files is the Project Gutenberg. If you go to that web address, you can find a lot of text files such as Pride and Prejudice, and these are the top 100 ebooks by today. I just grabbed this list. Frankenstein, these are the things that you can read for free from the Gutenberg libraries. But they also, you can now also download text files. And so if you want to test this with other files, you can use some of those files to see if your program actually works beyond the two files that are given to you. Any questions? The next assignment is going to be a topological sort assignment, and I will talk about that concept today. Okay. All right, so let's move on to the next topic. And there are a few things about this thing, like, for example, these are the things that you will implement. So pay attention to the red words in the document, where this is sort of like a function called load keywords from document. It takes a file, doc file, which is a text file, which is a document, and then it creates a hash map of strings, the words in that document, and the frequency of those words in the document. And but there's one thing that's very important for you to understand, that because documents have a lot of other words have a lot of things that you have to filter out. For instance, if you take the distance period, you have to strip off the period. So you got to figure out how to clean up the document. That's what the get keyword does. So you got to clean up these things, and you convert everything into a lowercase so that you know that rabbit with the uppercase or lowercase is the same word. It appears in a document. And if it's a noise word, you would not use that. That's a null. That you can find by looking at the noise word text and figure out that the word you get is a noise word or not, because you have a set of noise words that are in these documents. Okay. All right. So let's recall some. We are in graphs, and like I said before, the graphs are quite useful and quite important data structure. In fact, one can say that graph is the most important data structure that one can learn and use in many situations, because many of the real world problems can be modeled using graphs. Okay, so there are a few terminologies, like self-loop is a sort of like an edge that connects a vertex to itself. We call two edges are parallel if you have two edges between the same nodes, which we usually don't consider these kind of graphs because we assume that there's a unique edge between any two vertices. But this could happen in a real situation, and that would be more like sort of like you have a connection between two things, but you could have maybe two paths or something. So you could imagine something of that sort, but not always something that we consider. But you could apply many of the graph algorithms to these things. So I'll come back for the questions at the end or at a break. Okay, so just hold on to your questions. So when an edge connect two vertices, that we call them adjacent. So if you have two vertices connected by an edge, we call them adjacent vertices. And the degree of a vertex is the number of edges incident to it. Like, for example, if you take a vertex, and if that vertex is connected to three other vertices, then we say the degree is 3. And this degree is 1, degree is 1 here, degree is 1 here, because it's connected to only one other vertex. All right. And a subgraph is a subset of a graph. So for example, you might have a graph like this. So let's say this is a graph, and a subgraph would be some portion of it. So you can break out a subset of the graph's edges to get a subgraph. And so subgraphs are really like in a matrix context, they are really like a submatrix if you think about the representation. A path in a graph is essentially a sequence of vertices connected by edges. So that's called a path. So you could find a lot of path from, oops, not this one. So you could find a lot of path from one vertex to another. That's possible. A simple path is a path with no repeated vertices. So you could have a path where you have no repeated vertices. But if you have a path going from here to here, here to here, and then come back here, now you're going to have a repeated vertex, which is also a path, but you have a repeated vertex. A simple path is a path with no repeated vertices, and that's the interesting part of this. A cycle is a path with at least one edge, whose first and last vertices are the same. So you could think of a cycle as one of these things. So cycles start from here, go to the next one. That's a path, that's a path, that's a path. And so if you take a cycle, in fact, any node is in a cycle here, because you can start from any node and go to any other node in the cycle, as long as you have the directions are working. Okay, and a simple cycle is a cycle with no repeated vertices. So we don't repeat vertices. And the length of a path or cycle is the number of edges. So if you have something like this, the length would be 2. So the length of that path is 2. In fact, now we'll be talking about what's called the Dijkstra's algorithm next week. And in that algorithm, we'll talk about the shortest path from one vertex to another vertex. We say that one vertex is connected to another. There's a path that contains both of them. So if you want to know two cities are connected, you might be able to find a path through other cities. So something like this could apply to like a Google Maps or something. The graph is connected if there's a path from every vertex to every other vertex. So for example, this is not a connected graph because you have two components that are disconnected. But you do have two components that are connected to each other. But if I add another edge between these two disconnected components, now you have a connected graph. All right. Okay. All right. Looks like my My computer froze, so I have to wait just a little bit for it to come back. So if you have any questions, I can just try to answer them. So you can you can type any questions on things we have done so far. Hello, can you hear me? Thank you. I apologize for, I'm pretty sure that it's probably on me. I probably lost my connection or my computer crashed something. And that's one of the reasons I think this is a very, not a good way to do things, but this is where we are. Okay. So, all right. So I'm not sure why that's the case. Okay, just 1 second. I'm just getting things started again. Okay, I'm waiting for my document. Okay, so the last thing we did was we looked at the connected graphs, set of connected components, and we can, given a graph, we can find a set of connected components in a graph. And given a graph, you could find more than one connected component. And if you draw an edge between two of the disconnected components, you could make this completely a connected graph. An acyclic graph is a graph with no cycles, and we call that an acyclic graph. The graph with no cycles, usually this is applied to directed graphs. So for example, if you take this graph and this cycles, but if you take this graph, this is not, so this is acyclic, and this one is not. So because that second graph has a cycle. A tree, essentially, what we know as trees are acyclic graphs. So if you think of a tree, the tree kind of, even a binary tree is an acyclic graph, because these nodes could have more than two nodes for things. A forest is a disjoint set of trees. So you could have a set of trees, and this a tree, you could have those trees. So forest. And those are terminology that is important, and I might refer to them as we go. Okay, so let's talk about our first algorithm, which is called the Dfs Search. I may have talked about this before. The basic idea is that I think it's easier to understand if you think about a maze. So in a maze, you might say, okay, I have this maze, and I want to find, I will define a graph in this maze like a vertex is an intersection. So that could be a vertex, and that could be a vertex, that could be a vertex, and so on. So the intersection means that, something that meets two roads or something. An edge is a passage. So for example, you could have a passage between those two edges. So one question you can ask is that can we explore every intersection in the maze? So if you explore every intersection in the maze, you actually create an undirected graph. So another way to represent a maze is now as a directed graph. In other words, if you knew that you enter the maze from that intersection and you want to go to this intersection, then you might try to find a path through these nodes to get to that place. And so you can see that that's quite important in terms of understanding how we take an interesting problem like a maze traversal and then convert that to an undirected connected graph. So if the question is that, is there a path from some vertex to some other vertex, that can be answered by traversing that graph and figuring out a path. Now, clearly, there are more than one path from one vertex to another vertex. But you might ask the question, how can I find then the shortest path? All right, so in terms of finding this kind of a path, first we talked about this algorithm called Dfs Search. So in the Dfs Search, the algorithm is quite simple. So when you go to a vertex, you mark that vertex as visited. So let's suppose that I start from 1. So I will mark that as visited. All right, so you can keep track of that in an array of visited nodes, that's for example. So you can keep track of those things. And then from that node, you will try to recursively visit all the unmarked vertices adjacent to V. But there are 3 vertices adjacent to 1 in this case. Those are 2, 7, and 8. And I might pick to choose any vertex here. So it doesn't have to be, I think the order could be determined by order in the adjacency list, which represent this graph. Or you can say, I'm going to go to the one with the lowest index. So I will go to 2. Now from 2, you're going to keep going. You're not going to worry about 7 and 8. So from 2, I can go to 3 and 6. But again, I will choose the lowest one to go, which is 3. And then from 3, I can go to 4 and 5. And in this case, I will choose to go to 4, which is the lowest index. So what you see is that 1, 2, 3, 4 is a path which is given by the DFS. So that's one path. All right. And because it's recursive, you could backtrack and go in the next path to 5. So you can imagine that you have path from 1 to 2, 3 to 4. You also have a path from 1, 2, 3, 5. So that's another path. Also, you can backtrack from here and go to 6. So you have a path 1, 2, and 6. And then you can backtrack from here to 1 and go to 7. So you have a path 1 and 7. From this side, you can try to go to 8. And then because it's depth first, you go as deep as you can go. So one path would be 1, 8, 12. Right? What would be the next path that that we will get? Can you type it in? Okay, great. So it could be 1, 8, 9, 11 or 1, 8, 9, 10. If you follow the precedent, I guess, the heuristics, that I will always go to the lower one, I would go to 8, 9, 10. But not 11 is not incorrect. So that's okay too. All right. So that's the idea of depth first search. Now, as you can see, I started with 1. My function, this is very, very simple to implement here. Only thing you need is, like, if it's unmarked, that means if you haven't gone there before, you will go there. And therefore, you're not going to repeat a path that's already been found. So let me ask you the question about the complexity of the DFS search. So what is the complexity of DFS? You can type the answer. Now, we always want to, when we would talk about graphs, we talk about the number of vertices and number of edges, N and E. So what would be the complexity of DFS? Okay, so I see the answer is like N plus E. That is good, because in this case, we're going to touch every node at least once and every edge exactly once. We're not going to process an edge more than once, but you might look at a vertex more than once. But it's some multiple of, so it's N plus E is the correct answer. So in other words, the complexity of DFS, that means to go through every vertex, would cost you N plus E, where N is the number of vertices. Now, if you recall how we connect this to trees, a tree is also a graph. And in trees, we didn't really care about the edges. We only cared about, we said big O of N. If you're doing in-order traversal, post-order, pre-order traversal, it's going to be big O of N. Right? That's the number of vertices in the tree. Okay, so here's the implementation of the Dfs Search. I've shown you only part of it, but if you go to my Sakai page and look for the code, you might find this piece of code. So here, the DFS is performed on a graph data structure, starting with a vertex V. And we say, okay, because we touch V, we mark the V as true. And then we get a list of vertices adjacent to V. And then if those vertices called W are not marked, then you would perform DFS on those things. So essentially what I showed you by drawing things can be implemented using Java with something like this. It's fairly straightforward. There are other things you need, such as the graph data structure and those kind of things. But once you have that, the algorithm itself is quite straightforward. Whenever you go to a node, you want to mark this as visited so that you don't put it back on the. So one way to think about this is the following. Okay. So let's say that we have. Let's take a simple graph. Okay. So let's take this kind of a graph. All right, so we have a directed graph here. So let's suppose that we start from 1. Now, this is recursion. You can see that I'm calling DFS from DFS. And recursion creates a stack. So if you really want to think about this from the first principles, you're really working with the stack. So the first thing you're going to do is that put the 1 into the stack, the element that you're starting from. And then you're going to find another adjacent node. So let's say 2, we put the 2 into the stack. And you find an adjacent to 2, let's say we found 3. We put the 3 into the stack. And so these are all marked as visited. So let's suppose that they're all marked. We maintain some kind of a data structure to do that. It could be a simple array. And so we marked because we have been there. And then from 3, you would go to 5. So now if you look at this, what you have is essentially a path inside the stack. You have the path is going to be, if you pop the stack, the reverse order of that stack is the path. So you mark as visited. So first you pop 5. When you go back to 3, you get to go to 4. So here's another node, another path, which is 1, 2, 3, 4 in the reverse order. So so basically, I think what we're saying is that it is really a DFS is a stack, because it's a recursion is a stack anyway. So you mark it so that you don't go back to 5 again. That's why you mark this as visited. Because if you don't do it, you might return to that when you take the adjacency list, things that are adjacent to it, you might return to that. Okay. All right. So what I'd like you to do is now, starting from G, perform, let's make it a directed graph. Okay, so we have a directed graph. So I'd like you to, starting with G, perform the DFS. Come up with, if you get an answer, you can type it into the chat. Now, when you try to decide to go from, notice that the nodes have labels like G, and also it has some kind of a number 1, 3, 5. So when you decide to go from one to the other, you might want to choose the minimum one, for example. If you have two choices, just go to the minimum one first. Okay, so follow that heuristic to go there. Now, in fact, if you really think about this, you can, well, there should be another note here. In fact, if you look at the adjacency list representation of this graph, the G is connected to A, and A is connected to R and N is connected to, there's an H from N to G, and then I is connected to nothing, and R is connected to L and K, and K is connected to B, and L is connected to N, and B is connected to L. And also, what else I'm missing here? Okay, N is connected to nothing, and A is connected to N. So you can see that the way I wrote this, in fact, what you're seeing is the representation of the graph. Okay. So now there can be, like I said, use the heuristics. So use heuristic to select the lowest index. That means if you have a choice between 3 and 4, you should go to 3 first. N is connected to I. That's correct. Yeah. Thank you for letting me know that N is connected to I. Okay, so this is the adjacency list representation. That's your data structure. So let's see what we can do. So we're going to start from G. And now we can go to A. That's the only one we can go to. So we go to A. And from A, I have two choices. I can go to either R or N, because N has the index 4. I'm going to go to N. So I'll go to GAN. And from N, I can go to either K or I, but I will choose I because that has the lowest index. So that's the so that's one path that we can get from the Dfs search. Because from I, you realize that when you go to I, there's nothing. You cannot go to any place because it's null from that list. And now from I, you got to backtrack to N. So you will backtrack to N and start going in another direction. So now, because now this is going to be marked, these are all marked because we came from those things. These are going to be marked. And from N, we will go to K, because K is the next, the K is the only one I can go to. Where I put the, okay. And then from K, I can go to V, because that's the next one I can go to. From V, I can go to L. And from L, I can go to N, and that's another path. All right, so obviously GAN. So once I go to N, I get stuck. And I will backtrack to this one, L. So I'll see if I can go to another one from L. I cannot go to another one from L. So I will have to backtrack more. So this time I'm going to backtrack to V. From V, I cannot go anywhere. So again, I'm backtracking. These are marked. Backtrack to K. Now backtrack to N. And from N, I'm going to try to see if I can go to any other path. I cannot because these are all marked. So I'll backtrack to A eventually. So this is the place that I can start going again. So from A, I can go to R. And from R, I can go to K. Again, I'm going to choose the smallest one, so I will go to L. And from R, I will go to L. And then from L, I can go to N. And from N, I'm done. So I'll backtrack. And N is 4, N is not 8. What do we say? Oh, there's 2 N's here. Oops. Oh, yeah. Okay, that's true. There's a little bit of a confusion here. But hopefully you got the idea here. Essentially, it's like finding a path. You know, you go backtrack when you get stuck, you go back. All right. But I think I will ask you to kind of go back to the algorithm. Maybe this is the best way to kind of follow the algorithm and see if you actually get this thing right. Okay. Now, what I marked is not, basically, usually when you do when you go to I think I don't even have a thing here. So the adjacency list is the one that we'll be using. Let's do another one. I guess that's probably okay. Let's do this one here. Now I like you to start from C, and it's an undirected graph, so I can go to anything adjacent to it, and basically, if you want to kind of show the order of visiting. Okay. At least this graph doesn't have any repeated nodes. The other one had, so that's why it's a little confusion there. All right, so take a little bit of time to see if you can start from C and do the DFS. Okay. Again, so let's see here, C, and I'll go to A next. And from A, I can go to B and E, so I'll go to B. 1, 2, 3. From B, I will go to D. So now I'll backtrack to B and then go to F. From F, I can go to E. And from E, I'm not going to go to A because that's marked. And so after E, I'm going to backtrack to F, backtrack to F, backtrack to A. And then, let's see here. Where's the C coming? Oh, yeah, backtrack to A, backtrack to C, and then I'll go to this one here. So it'll be like the next one will be C and G. All right, so I can find 2 paths by going through Dfs Search. So 1, 2, 3, 1, 2, actually 3 paths, right? So 1, 2, I went to CABD and then CABFE, and then I will go to CG. I'll backtrack all the way to A and then C and then go to CG, and so you're done. You covered all of the paths in this by doing DFS. Now, notice that if you really want to, so I'll get to that. I think it was about detecting a cycle and stuff like that, but that's DFS. Okay, let's go to the next one because I got a few things that I need to do. Okay, here's a little poll here. Let me just try to turn on. Okay. Oh, I can't. Second here. I'm trying to turn on the poll. Poll So 4 answers here. All right, so it looks like most of you are getting this. So the correct answer is the sum of the degrees of the connected components, because when you do Dfs search, you can only go within the connected components. So sum of the degrees, if you look at a degree of a node, is the number of edges connected to it, and so it is the sum of the degrees of the vertices. All right. Okay, so the next idea of traversal is called the breadth first search, which is called the BFS. So what we do is, we're starting with any node, you explore all the nodes adjacent to it. And in fact, there's a good application of this, is called the web crawler. For instance, in the early days of Google, when people are sleeping, what the Google did was to start from some famous web page, like CNN.com or something like that, and then go to all the things that are adjacent to it. And then from there, it goes to all the things that are adjacent to it. Now, in a tree, we call this a specific traversal. What was that? Any ideas? What is this called in a tree, that kind of BFS? It's called level loaded traversal. That's correct. Okay. So the implementation of a level loaded BFS is also very simple. What you do is you enqueue your starting vertex. So let's say we have a queue, we enqueue that. All right. So your queue has only one vertex. And then inside the loop, while the queue is not empty, in this case, queue is not empty because you have one node. And you, for all u adjacent to in the queue, for all, sorry, all, I think I should say G. So you find all the nodes that are adjacent to V. Find all the nodes that are adjacent to V. So we dequeue A. So we write A. And then we write all the nodes that are adjacent to A into the queue. So in this case, we're going to put BCE into the queue. So your queue has now, so notice that it's Q and QU. Take all the nodes that are adjacent and put that into the queue. Then you go back, because the queue is not empty, you're going to dequeue B, and then look at all the nodes that are adjacent to B that are going to be D and F. So we put them, those things. What's the cost of finding all the nodes adjacent to a node? So the question is, what is the cost of finding all the nodes adjacent to a node? Cost of finding all the adjacency nodes to a V. So given a node, what is the cost of finding all the nodes that are adjacent to that node? O of E, okay, any other answers? So one answer is the number of edges proportional to the edges. Okay, so in fact, this cost is very easy to compute. If you typically, all the graphs are stored as adjacency list. And so if you take a node V, all of the adjacent nodes are here in that node. Okay, so the answer to this is it is the degree of V. That means those are the nodes that are connected to V. All right, so that's, in this case, it would be 3. So the cost of finding this one is going to be the degree of the node itself. All right, any questions there? All right, so let's move on to the next ones. Okay. So in code, so here's the code for breadth first search. It's a little bit more involved. Again, you have some data structures like a graph, and you're starting from this node S, and then you have a queue of integers, and so if you can easily, this is Java code that does it. So it's not difficult to find these things. I mean, difficult to implement the BFS. All right. So what is the cost of Bfs? So what's the cost of doing BFS? Very good. So the cost of doing BFS is n plus e, the number of vertices plus the number of edges. Now, typically, if you really want to simplify this, you could write this as big O of e, because usually the number of edges are much larger than the number of nodes. That's always the case. If you don't have that, in fact, if the graph is a tree, if the graph is a tree, what is the relation between n and e? If the graph is a tree, what is the relation between n and e? N is the number of vertices and e is the number of edges. N squared 2n e plus 1 equals n minus 1. Okay, I like that. So in fact, the number of edges is n minus 1. Because if you think about a tree, any tree, take a tree. This tree has 4 edges and 5 vertices. So the relationship between, in fact, if you have a graph where the relationship is e equals n minus 1, it is a tree. Okay. So let me go to the next concept here. Okay, can you perform, let's take a few minutes to perform BFS on this graph. It's an undirected graph. And, oops, what did I say? Node from D, not from D. I want to start from 6, node 6. If it's an undirected graph, I can start from any node. And if you look at this, this is a totally connected graph. That means I can go from any node to any other node. There's a path that you can find. Okay, so let's see whether you could do BFS on this one. So remember, the BFS is called the level loaded traversal. So I'm going to call this level 0. Okay, 6 is level 0. That's where you start. And what are the nodes in level 1? Okay, so the level 1 nodes, there's only one node in level 1. That's the node number 2. So that's level 1 node. What are the nodes in level 2? Level 2 nodes are the 5 and 1. Those are level 2 nodes. And level 3 nodes are, these are level 3 nodes, and also these are level 3 nodes. That means, in some ways, what we are saying is that you can go there in 3 steps, 3 hops, right? If you start from node 6, and this shows you the length, the path length from 6 to every other node. And these are level 4 nodes. And these are level 5 nodes. So if you really want to draw this tree in a different way, you could draw it like this: 6, then you draw the level 1 nodes that are 2, then level 2 nodes are 5 and 1, and level 3 nodes are 9 and 10, and level 3 nodes I have 3 and 4. So notice that I'm really reshaping, I'm redrawing this graph, but it's the same graph. I really haven't changed anything about the graph, the properties of this graph, right? So basically the BFS, in fact, BFS will be useful to find the shortest path from a given node to any other node. Like if the question is, what is the shortest path from the node 6 to node 11? What is the answer? I want the shortest path. And in this case, I take each edge as a path 1. So what is the shortest path from 6 to 11? It's, yeah, shortest path. It's so you have 6 to 1, 4, 7, 11. Yes, that's right. So you have 6 to 1, 4, 7, 11. And the length of this path is 5. And the length of the path is already there, because you can write each node can have a distance. So in this case, doing BFS, you can find the shortest path from one vertex to any other vertex. In fact, the numbers you see on the graph are the shortest paths there. All right, let's move on to the next topic. So the next topic is called topological sort. The topological sort is given a set of tasks to be completed with precedence constraints. That means you will say A must be complete before B. So if there's an edge from A to B, that means we say that A must be completed before B. Now, this graph you're seeing on the screen now is a directed graph, but it's a graph that is very important to you. What is this graph? I'm sure some of you have seen this. These are the requirements. So in this case, 111, and you're in 112. And from 112, you can go to 211, or you can go to 344, the algorithms course. All right, so it shows you a directed graph that flows in only one direction. It goes from the top nodes to the bottom nodes. So there are a lot of paths here that you can take in order to complete a sequence of courses. Now, the question you might ask is that how would you label these things so that you know that you must complete 211 before you can take 314? All right, so those questions can be answered by this idea called the topological sort. All right, so that's what we're going to be doing. In fact, it's a very useful algorithm for finding scheduling, for example. So if you have very complex number of tasks that people have to do, and you want to know what is the order of these tasks, and you can order them. Okay, so we'll talk about that in a little bit. So how do we do that? So essentially what we need to do is we go from a graph with some constraints. That means you can start from 0 and go to 1 and so on. So if you think of 0 and 1 and 5 as tasks, you must complete 0 before you can complete 1. You must complete 1 before you can complete 4. So the question is, how would you take that and put it into a form like this, which is a flexible schedule? In other words, given the left graph, it's hard to say what these things are, but given the right graph, you can actually have a variety of things. You know that the first task that needs to be started is 3, and then 6, and then if you order them 2, 3, 4, 5, 6. So you could order the vertices in that order, so that what this says is that without completing 3, you should not go to 6 or 0. You couldn't go to 6, right? So the idea is that when you look at the left-hand graph, you feel like I got to start from 0. But if you start from 0, the 3 is kind of stuck. You are not able to complete 3, because you have to complete 3 and 6 in order to complete 0. So you shouldn't start from 0. Okay. So how do we do this? What is the algorithm for doing that? There's a simple algorithm for doing it. For this algorithm to work, topological sort exists only if your graph is a directed acyclic graph. We call it a DAG. So it's a directed acyclic graph. Now, if it's a DAG, then you can find a topological sort. Okay, so we ask the question, is this a DAG? And the next question is, how can we find cycles in a directed graph? Because in order to prove a graph is a DAG, you have to show that the graph has no cycles. So the graph given here, is this a DAG? Okay, so yes. How do we know that? So what is the algorithm for finding a DAG? Finding a cycle, actually. If you can find a cycle, because we know it's a directed graph. Can you suggest an algorithm for finding a cycle in a graph? DFS, that's correct. So the idea of finding a cycle is that you can start from any node, say 5, and then you do a depth first search. So let's say from 5 you go to 11, you go to 2, and you couldn't go anywhere. So backtrack to 11 and go to maybe 9. And maybe 9 you may have a link back to 5. So suddenly you have now, in other words, when you're creating the DFS path, you have 5, 11, 9, and then 5 appears again in your path. That means it's a cycle. So if I add the edge from 9 to 5, the DAG becomes, it's not a DAG anymore. Okay, what is the algorithm for finding a DAG? In fact, the topological sort. So this is going to be your assignment. Not this particular. So I'm doing this with the DFS, but your assignment is going to be mostly on BFS. So the idea would be that you run the DFS. This is to find a topological sort, and then you return the vertices in the reverse post order. All right, so let's apply that to this algorithm here, this graph here. So because we know this is a DAG, we will be able to find a topological sort, which is essentially a relabeling of the vertices to show some kind of a order. So let's suppose that we start from 5. So we start from 5, then we go to 11. And from 11, we go to 2. Now, we call the post order means that the last element that you go to that you cannot go anywhere is the first one you're going to output. So you output 2 and backtrack to 11. From 11, you go to 9. Now, because you cannot go from 9 to any place, you will output 9. And that's done. And then you go back to 11. From 11, you can go to 10. Because you cannot go from 10 to any other place, you're going to output 10. And that's just called the post order. You can imagine these are like the number of vertices that are removed from the stack. And from 10, I backtrack to 11. And from 11, I cannot go anywhere. So I'm going to start with a different vertex number. So let's say I'm going to start with 7 now. From 7, I go to 8, but I cannot go anywhere. So I'm going to put that into the stack, put that into the path, into the post order. And backtrack into 7. And so the 7 comes next. And now I'm going to, I only have one thing left, which is essentially 3. So now this is essentially order. This is called the post order. Called the post order. So the topological sort is given by a reverse post order. So we're going to reverse this list. 3, 7, 8, 10, 9, 2. All right. So if you draw the links from the original graph, we have a link from 3 to 8. We have a link from 3 to 10. Then from 7, we have links to 11 and 8. Where's the 11? I'm sorry. What happened to 11? I think I missed 11, right? Let's see here. What happened to 11? In fact, 11 would be, yeah, I think I shouldn't have ignored 5 and 11. I think they are going to come around, where it is going to come, I think before 7, right? So at 7, before I went to 7, so after 10, even before 8. I made a mistake here. I apologize for that. Let me do this again, because I think it's probably a good idea to redo this because I made a mistake there. All right, so let's go from 5, 11, 2. So you get 2. Backtrack to 11, you can go to 9. You cannot go anywhere from 9. Backtrack to 11, you can go to 10. And backtrack to 11, you cannot go anywhere, so the 11 should come here. And then now we're going to start from 7. From 7, I go to 8. 7, I go to 8. And backtrack to 7. And then I will start from 3. So I believe that's correct. Okay, do I have all the elements? 6, 8. Nope, I'm still missing one. What am I missing here? I still messed it up. I am really sorry. Let me just do it again. Okay. So 5, 11, 2. So let's go to 2. Backtrack to 11. And so 2 is that. So from 11, I can go to 10, but I cannot go anywhere from 10. So I'm going to put the 10 in there. Backtrack to 11, I can go to 9. So I have done 10, 9, and 2. So from 11, I cannot go anywhere, so I should output 11. And then I came from 5, so I should output 5. And now I'm going to start going from 7. I can go from 7 to 8, so the 8 is the next one coming. And then backtrack to 7. And from then I go to 3. 3 is the only one left. Now I got 8, yeah. Okay, so let's reverse this. this is called the post order. So 3, 7, 8, 5, 11, 9, 10, 2. So if you draw links from 3, I can go to 8 and 10. And from 7, I can go to 8 and 11. And from 8, I can go to 9. And from 5, I can go to 11. And from 11, I can go to 2. And then from 9, I can go nowhere. That's it. I think these are all the edges I have. 1, 2, 3, 4, 5, 6, 7, 8. I hope I have 8 edges. If I didn't draw anything, you can complete that. Okay. So you can typically what you do is you have to have this post order, and this is called the reverse post order. That you're just reversing it. Called reversed post order. All right. So reverse post order gives you, notice that in the reverse post order, things flow forward. So if you take this complex, okay, what are the questions here? Can someone 5 to 8? Okay, asking 5. How'd you go from 5 to 8 to 8, 7, 3? Oh no. So after 5, you're going to start from a new DFS. Okay, because you look at the things that you haven't touched yet, right? Because you put the you got an order here, but you look at the things that you haven't touched yet, and you could pick 7 or 3, doesn't matter. If I pick 7, I go to 8, and so that's why the 8 come next. Then I backtrack to 7. Then I go to 3. Now I could have done this in a different way. I could start from 3. And if I start from 3, you would still go to 8, and then 3 and 7. So that's another topological order. And so it's not unique. Okay. All right. So there are multiple ways that you can go. It's not unique. So in other words, this is a very important thing. If you really want to practice this, I will ask you to take this and see if you can do a topological sort on this one. This is probably something that you care about, right? See if you can do a topological sort on this. So in getting started, it would be more like I'm going to start from 111. So let's say I'm going to start from 111, then I go to 112, then I go to 344, then I go to 452. So the first node I will output is 452. All right, then you backtrack to 344. Can't go anywhere from that. And so you are going to output 344. Okay, so I'm finding the post order here. And then you go back to 112 from 344. And from 112, you can go to multiple places, right? You can probably go to 334. But from 334, you cannot go anywhere. So you're going to put the 334 here. So what I'm doing is I'm finding the post order of your requirement map. So by doing this and reversing, so obviously I'm finding the post order, I have to find the reverse post order to get the a topological sort. But you can find a topological sort here because it is a DAG. Okay, it's a directed acyclic graph. So why don't we do that? Just do this, and then when we meet on Tuesday I'll probably do this before you guys come, and then we can compare the answers. Okay, so just do the topological sort for your requirements thing. Okay, a few minutes left, 3 minutes. You can ask any questions. Graph algorithms are very useful and really a lot of applications on that. Okay, little search engine, yes. I think the insert last occurrence method, not really sure. I think you should, let's see, where was that? I think the write-up was fairly complete. What you're saying. Where is the insert last occurrence? Okay, looks like someone already answered that. I think the binary search is done because you're going to keep the basically, I think, yeah. So when you build the so this structure here is a bunch of keywords and a list, an array of pairs of things, right? You have a word and the frequency, but you keep them in sorted order. So notice that the 2 and 1, you keep them in the sorted order. So if you do binary search, if you get a new document, so let's say that you had a new document here, let's call that, I don't know, X or something, with a frequency 3 for the word world. And in that case, you will insert that into the correct location. I believe that you have to do binary search to find that. You do the binary search on the frequency. Okay, so I think we will wrap things up here. And what I will ask you to do is to really try to implement the BFS and DFS, at least try to understand that. The questions, some other questions I see here. Can we chain BST to a hash table, hash index instead of a linked list? Sure, I think you could do that, but that's not what the assignment is asking you to do. If you can do that, I think the only problem is the hash BSTs are more complicated to maintain, and a linked list or an array is a simple one. Okay. All right, so I'm going to wrap things up. If you have any questions, you can either email me or something, because it looks like we're past 8 o'clock right now. So, all right, so I'll say good night and see you Tuesday. Bye-bye.